A rather common type of problem that you can solve using logarithms are problems that are asking about the half-life. Now, the half-life of something is how long it takes to decay until there's half as much left. So the most common thing you run into is the half-life of radioactive matter, because if you start out with like 10 grams of uranium, then after, 24,000 years or so, you're only going to have 5 grams. So what you can do is calculate how long that's going to be lurking around in, in your soil or in your area. Another really common application is calculating how much of a medication is left in your body. If the half-life of a cold medicine, like Tylenol, is 8 hours, and you take a dosage, then after 8 hours you still have half a dosage worth floating around in your blood. And this is good to know because this is good to know as a doctor or as a person so that you can, think about how things might be interacting in your body. So, let's consider a substance that has a decay rate of 5.6% per unit of time. We want to know how long it will take until we just have half of the amount of substance left. So, there are two types of equations this could fall under. One is the plain exponential equation, y equals a times b to the x, and the other is y equals ae to the kt power. ae to the kt is for continuous growth or decay, and if it's continuous, the problem or the situation will sort of make this clear. So in our problem, nothing about this mentions that it's continuous decay, so we're going to use y equals a times b to the x. Now, we need to identify a few things. One is, this is regular growth and continuous growth. Now, we need to identify the final amount, our starting amount, our decay factor, or, growth factor, and what x stands for. In this case, time. So time is what we're looking for. I'm just going to put the variable in for that. Our decay factor is 1 minus our 5.6%. If this was a growth factor, we would do 1 plus our growth factor, which is 0.944. So remember, decay factor, you subtract your decay rate from 1. If it was growth, you would add your growth rate to 1. Now we've got the starting amount and final amount, but I don't have any information in my problem to help me out with this. So let's think about it. We're interested in how long until we have half the amount of substance left. So if I were to start with 20 units of something, then when I had gone through one half-life, I know that I would have 10 units of that thing. Or if I started with 4 units, at the end I would have 2. Or if I started with 32 units, at the end I would have 16. So it's really up to you, whatever you feel like using for the starting amount and ending amount. So I feel like starting with 10 units, and at the end I'm going to have 5. So let's put these into our equation. I have 5 units left at the end, and I'm going to multiply that by 0.944 and raise it to the t power. Now how do I solve this? Well, the first thing I need to do is divide both sides by 10 to get my exponential phrase by itself. Then I can take the natural log of both sides, or the regular log of both sides. Now what can I do? My exponent, or my variable is still in the exponent, but because I now have logs on both sides, I can use my properties of logs to get that variable down. My last step is to divide by 0.944, and the problem is complete at this point. Or I can go on and say that it's going to take 12 units of time until I have half of the amount of substance left. Now this problem is going to work out the exact same way no matter what starting amount you put in and what final amount you put in. So the key points here are the need to identify what information you're going to use in a problem, even when it's not stated in the exact word problem, and also that when you have a decay factor and it's not continuous, you subtract that rate from 1, and if you have growth, you add that rate to 1.